What is a group?
What's the
What is a group?
Like 14 times sometimes in single sentence.
It's non-empty set with
This
one
literally happens to me.
operation that is
No, I
close to
get
that
it.
What's an
operation.
operation?
I don't feel stressed.
It's a board game. Yeah, go ahead and put that on the test if you know what happens.
He probably would just be like, you know what? -5.
Correction of
Correction.
original.
I can see him doing it.
I can see him doing that too.
-5.
If only you were in the class, that way you could actually get that grade. I mean, I'd be so proud if you got a negative score.
I would be impressed.
It would be impressive.
Write something so bad it takes points away.
Yeah.
-5.
Also, the universe is 18.
I didn't finish the thing. He interrupted with what was an operation and class is something, so.
Operation can be.
I didn't even say that it
Actually,
needs
no.
to be.
It's a good
Well, then
question.
it needs to be associative. I didn't get any of it.
What, you know, each of the words that you use in defining a group has its own definition.
Define is. Yeah.
Okay.
Well, now we know it works.
Explanation.
Define the word define.
No. This was, well, Willy Wonka. Divine explanation. You remember that?
Yeah, it's defy, not define.
It's divine. Wait, it's not, it's
It's
divine.
define.
It defies explanation because it's magical. It can't be explained. It defies.
Are you sure it's not
It's
divine?
defy.
Nah, everything I know is a lie.
It's funny how often some lyrics are like that.
Yeah.
I have this song,
You're right.
There was a Dave Matthews song.
I have a lot of
It was
songs
called
that
Send Me On My
happens to.
Way.
Yeah.
And I swear, for a long time, it was Singing and the Whale. And I'm singing the whale.
Oh, there's a movie that makes fun of it.
Everything I know is a
Something in
lie.
something about boots song and they sing it wrong. It's some romantic comedy.
It's just, when you finally find out what the correct thing is, and people laugh at you, it's not a good one.
Like that one song that's not about Tony Danza at all, so it's actually about a tiny dancer.
Well, what's actually really bad is when they post wrong lyrics on like a YouTube video or
Yeah.
something, and you're like, I totally can't even think of the real lyrics because this sounds so correct.
Indeed.
Like you know they're wrong, but you're sitting there going, how is this song really supposed to go? I can't remember.
Wow, I'm terribly tempted to put up this YouTube video of a band that spoofs the Bee Gees, like these disco era songs, and they have these horrible fake teeth in there.
Yes.
Do one short video, or if you don't have time, then no. Oh,
Yeah. We have like 12 more
we
mathematicians.
do have a lot of
in 5
mathematicians
days.
to get through.
No, we have, Kevin today we have 7 days.
Although I
Monday, Monday,
I
Wednesday,
gotta
Friday.
say, I was watching The
Just
Big
Monday, Wednesday,
Bang.
following.
I gotta say, I was watching The Big Bang over the weekend. They were watching a documentary on Tesla versus Edison. They said their few totally beats Newton versus Leibniz, and I just laughed. I was like, I know what they're talking about.
That's good. So, I want to start today by mentioning that we have some celebrities in our midst here. The team of people that went to the MAA conference over the weekend just rocked. David Diaz and Michael and Devante were a team on the math competition. It was the first time that any team from Southern has played in a math competition. Which figures because it was the last time I was part of running it, so.
You're welcome.
Alright, so let's give us a round of applause. I started it.
I would have applauded you, but you started your own, and that's just sad.
Yeah, that's
When you have like if Yale or Brown or Harvard sends a team, they're gonna take first place. That always happens.
Right.
And this time they didn't, so maybe that's.
No, they totally did, and we beat them.
And you beat them. But yeah, there's a lot of good schools in our section.
Ain't that interesting?
Where did you guys place it? Where did you guys place it? This
No, we're good.
But, and then you were first in the scavenger hunt.
Indeed.
And that was all of you? Or was that?
That was
It wa-
them, and then I was the honorable mention.
You were the honorable mention?
I don't know why.
That's actually a good question.
I don't-
Maybe you came in fourth?
Me? I don't know.
Or maybe you got all the numbers right.
Can you please tell everybody how awesomely fun the whole thing was?
It's great.
It actually was very
That's
fun.
So take advantage of these kind of opportunities. The next time it comes around, go to one of these.
Yeah, if I don't have 2 tests on Tuesday, the next time it comes around.
Yeah, the
it'll be
timing
next
could be
year.
better.
It's next year.
Well, for the next thing we'll be doing in the spring will probably be the Hudson River Math Competition. And, yeah, look out for that. I don't remember when the dates are. I'm
It's
gonna
all
say
about
usually
timing.
end
If
of
it
March.
falls in nicely, I'll be happy to go. It's not like it was, but it did not fall in nicely.
I do, I think,
Why is
but
the
that's
problem happens
usually
fall
after
the week
school,
before
so
mine?
students typically don't go to that.
Ouch.
Yeah.
But of course,
But
people
that
are
would
welcome
make a
to,
great
so.
keyed up.
So you guys ready to talk about this dude, William Rowan Hamilton? There are several, there's actually one picture of him. He's alive when photography was in its infancy. So the photograph was horrible. You can't really make anything out. So that's a bust of him at Trinity College in Ireland, Dublin. And it does, I think, does a better job of representing his face than the rest of the art. That's him on a stamp. You guys recognize what country the stamp might be from?
Ireland. Northern Ireland?
Right, where Trinity College was?
That's the Republic of Ireland. EIR, the accent of it. So I guess it's a 48-cent stamp.
That's very prominent around.
Yeah, well, it extends very far up. That's how you.
No, it's like out.
Oh, you mean that
But
part,
it's
yeah.
like very-
Yeah. I don't know. This guy, this picture of him, or this image of him, he looks like somebody you'd like to hang out with. Like he'd be kindly and just a nice person. I'm like, he looks angry. Sour. Anyway, wanted to say a little bit more about Gauss before we move on to Hamilton. So, that whole topic of non-Euclidean geometries is kind of an interesting one. Even though Gauss didn't really, at least he didn't write down anything that made it clear he invented them. A lot of people do believe that he came up with these ideas. And you notice the word is plural, geometries. The one thing Gauss did come up with is called Gaussian curvature, which is the product of the principal curvatures. So if you're on a surface, you kind of scan around, you can kind of define a line, and in that direction, figure out the second derivative of the curve. You know, so you've got you've gone from a 2D surface to you picked a direction, and now it's a 1D curve, right? So you can calculate its derivative, you can calculate its second derivative. Just figure out what the second derivative is, and now rotate, and keep track of those second derivatives. Once you get facing this way, you're back to where you started, right? The line has just done a 180-degree end-for-end swap, so you begin seeing the same number you had originally for second derivative. So that guarantees you've got a periodic function. Periodic means that it repeats itself every so often. In this case, it repeats itself every 180 degrees. And a periodic function that, unless it goes unbounded, you can try to figure out how the curvature of a line could become infinite. That would mean you kind of like a point. You get a V-shaped thing. But if you've got a surface and you do this trick, the bounded periodic functions always have a minimum and a maximum. This is basic calculus. Right? So whatever those numbers are, multiply them, and that's called Gaussian curvature. If both those numbers are positive, Gaussian curvature will be positive. And that means you're curved this way, upward some amount, and over this way, upward some amount. In between, it may go to smaller amounts of curvature. But that was mine. Can can you picture what sort of thing we're dealing with if it looks like that?
It's
It's
a
a ball.
hyperbola with, parabola.
Just say ball. It does, locally it will look like a paraboloid, but you know, it's something that's got a low spot on it. And this is something if you did calc 3, you solved. Remember that horrible calculation you have to do to determine whether you're at a high spot or a low spot in calc 3?
The Hush matrix.
Yeah, the determinant of the Hessian. Well, that's also the Gaussian curvature. They're not quite equal, but they're related to one another. What happens if this blade's curved up, when we turn around, it's curved this way?
We have a Pringle.
It's a saddle, a Pringle shape. So those two kinds of curvature are what distinguish the two kinds of non-Euclidean geometries. Anyway, let's remember the fifth postulate from Euclid. They usually usually people quote it in a term different than the way Euclid wrote it. This is called Playfair's axiom. For every line L and point P not on L, there is a unique line L prime which passes through P and lies parallel to L. So usually there's a picture that goes like this. You've got your point P and your line L, and the line L prime looks like this. And it's uniquely determined. You know, think about it in terms of if you were doing this from like a pre-calculus perspective. If you're going to give me a line that's parallel to L, you have to have it have the same slope as L. And so once you know the slope and you know what point that it goes through, use that point slope form, and you can write down an equation for it. So the uniqueness of that line makes sense if you're thinking Euclidean. But this is about the axioms, right? And this is about, you know, we're thinking of these lines as quote unquote straight lines. What straight lines really mean?
Roughly using a straight edge.
Well, not really. Most of the time these days, if you want to construct a straight line, you use a laser. Because the straight edge will get bent. Can you bend the laser?
Depends what medium you're in.
Well, yeah, I guess true. You can run it through a lens or something. Okay, but you know, running just through straight,
Yeah.
let's say through vacuum, and well, until you get into Einstein.
We know what you're saying.
Yeah, you know what I'm saying. So that notion of straightness is the right one. Geodesics. They are the paths of they're the shortest paths that one can take in a particular space. So the shortest path between 2 points is a straight line. You've heard that before, right? Is it always? What's the shortest path between here and here?
You're not allowed to go through your head.
Yeah, we're not allowed to go through my head.
It's,
Then we got to go up and over, right? Or around the front. Which one's the shortest of them? I don't know. If you used a string and pulled it tight on my head, you put some pins into my head and then pull the string tight, and the string would lie on that straight path. That's called a geodesic. All right, so let's think about just this from a logic perspective. We would like to get geometries where the fifth postulate is not true. So we need to talk about what its negation is. And it's a unique existence. That's the type it is. That is where it says there is a unique line. There is one. There is one and only one line that satisfies that shape. All right. So there's two ways to say no to that. You could go with, there aren't any lines like that. There's no L prime. Or you could say, well, there's 2 or 3 or 4. There's many, right? At least 2 lines that satisfy that condition that they pass through P and are parallel to L.
so is the first one positive and the second one negative curvature?
There is no line is positive curvature. Yes, that's also called Riemannian or elliptic geometry. Okay, so this is me at the Museum of Math that you guys didn't get to go to, right? And I'm riding the square wheel tricycle. Actually, I stopped riding the square wheel tricycle when the man took the photo of it. But what actually I want you to see is what's in the background behind me. Now, it's a little hard to see. Can I zoom on this crazy thing?
Yeah.
No, if I do that, I go backwards.
Try some control clicking.
Wait. Control is something?
Control scrolling.
Damn it.
Control plus.
I don't think that works in this kind of power.
Okay, wait a second. we're just going to rely on your eyes to zoom in on this. If I had it on my Mac, I guess it would. But there's a display in the back that's called the Shape of Space. And there's actually several stations in it. But you see this one's a sphere. Can you tell what this kid is writing on right over here? He's taking notes for some reason on the display.
Jigger.
It's a jigger, yes. It's like a cylinder that's shrunk down in the middle. So it's got that saddle-shaped curvature on it. One way it's curving this way, and the other way it's curving up. So down on one direction, up on the other. And those displays are filled with holes. There's holes all over the surfaces of those things. And what happens, you hit a little button and it turns on a vacuum system and it starts sucking air in through those holes. So you can take stuff and stick it to the surface and it hangs and sticks there. It's really fun. And so if you try, you'll see there's like little baskets here with stuff in it. Those are very thin, flexible foam rubber polygons, triangles and hexagons and stuff. And you get to play with trying to put tiles on a sphere and have it all work out, right? And you'll notice that it doesn't. That's the interesting thing. Like if you're on a sphere, normally how many triangles do you get to meet at a central point on a sphere? Let's say you have equilateral triangles.
Points what?
Equilateral triangles. How many of them will come together on the surface of the sphere?
2.
There's an equilateral triangle. There's another one. Well, that wasn't very equilateral. We have 3. 4. Is it 5 that will come together? Or did I just draw sloppy? What angle is in there? These are equilateral triangles.
Oh, 60 degrees. So it has to be 60.
6.
So there should be 6 of them.
Yeah.
But if you try getting 6 of them to go in on a sphere, it doesn't work. What you're used to is 6 of them will work on a plane. Right? Okay. So you should go to MOMAP and play with that exhibit. That's the lesson. Here's the 2 shapes that they have there. This is a stolen graphic. And it's about the way the angles on triangles work if you're in these unusual geometries. So if you're in a hyperbolic space, it's as if you're drawing geodesics on the surface of a what's that shape called? That's the hyperboloid of one sheet. That's what its technical name is. But anyway, the thing that has any saddle-type curvature on it, you try to draw triangles on it, the angles, alpha, beta, and gamma, add up to less than 180 degrees. If you're in Euclidean, you all know this there, right? The angles add up to 180. If you're in an elliptic or a spherical or a possibly curved space, the angle sums are greater than 180. My favorite example of that is to talk about the following straight line. So, by the way, I just watched the Justice League movie. Anybody know that over the
I
weekend?
haven't seen it yet.
The end of it, there's a race between the Flash and...
Don't spoil it.
It's just the thing.
Spoil.
He's not going to say
Spoil away.
I wanted the race to go like this. They go up to the North Pole and race down to the equator, and then race around the equator, and then race back to the North Pole. Go like 1/8 of the globe,
Yeah.
because that's a triangle. Well, what are the angles on that triangle? If you go from the North Pole down to the equator, and then 90 degrees around the equator, and then back to the North Pole.
It's a ledge.
Well, you can. Let me try to draw it for you. You're saying jigger to everything now.
It's a ledge.
That's his thing.
That's Elon Musk question.
He used up all his brain power over the weekend.
We used a lot of it. That's our guy. He runs down like through the Greenwich Meridian. Then he makes a what angle turn do you make if you're coming down a line of longitude and then you turn to run down on the equator?
90.
90.
That's a 90 on there, isn't it? And then he runs 90 degrees around the equator, and then he makes another 90-degree turn, and then he goes back to the North Pole.
So it's 270.
So yeah, that's got 3 90-degree angles on it. But doesn't it seem like he was working on straight lines there? Straight, subject to the idea that you're on a sphere. Well, the truth of the matter is, you can't tell as a being living in a space. You think we're living in Euclidean space. I know you all think this. But how do you know? You're like an ant crawling around on that surface, you know? I mean, what are you going to do locally to measure that and realize that, oh, wow, I'm on a saddle-shaped thing? could possibly do. We don't have it. We're nowhere close to the technology we need to do these kinds of measurements yet for ourselves. You need to be able to measure curvature on a galactic scale because the universe we're in is huge. But one thing you could do is measure up triangles and see if the angles came out to be smaller or bigger than 180 degrees. And Gauss actually tried to do that. I think I already told you that story of the bonfires. Okay, so back to Hamilton. Another one of these kids that was just a real prodigy. Was a child who was, by the age of 5, fluent in Latin, Greek, and Hebrew. I mean, he was educated by his uncle James, Reverend James Hamilton. His father was a business person and was away off in England a lot of the time. The family was actually Scottish, but the Irish are very proud of him, I tell you. Remember the Irish stamp? I suspect the Reverend wanted him to learn Greek and Hebrew because those are the languages that the Bible was originally in. Why the Latin was in there as well? I think a lot of the Roman Catholic Church, the liturgical sort of stuff was in Latin. I'm not sure what else I have to say about this guy and his growing up. He was a prodigy. He was really smart and learned a lot. He became a wonderful poet. His poetry is actually quite good too. But the sort of sad and romantic story about him is he fell in love with a Disney girl. A Disney princess, really. This was a well-to-do family, but his family was good too, and he visited them at one point and saw the daughter of the Disneys, and it was just like, I can just imagine the heart beating out of his chest. He really liked this girl. But when he met her, he was an undergraduate student. He was the top of his class at Trinity. He was doing, they have a system that's sort of different from what we do. You don't have tests and quizzes and stuff through the year. There's just a big-ass test at the end of the term. And it's on everything.
Oh.
Everything you learn, 2 days of examinations. And then they grade you based on, is this the best thing we've ever seen in 20 years? If they can say that about you, you get a grade called optime, the best, right? Like optimization, that's the best. Otherwise, there's things like bene, bene is just But there's a whole stack of Latin terms they would use as the grades. He got an optime in 2 different subjects.
Wow.
And they weren't math. It was classics and astronomy. Well, I guess astronomy sometimes counts as math. But nevertheless, he was still an undergrad student, so he didn't have money. He wasn't ready to ask for the hand in marriage of this Catherine Disney. And just a year later, they announced that she's being married, it seems. It was an arranged marriage to a much older man who was a reverend. And so she's in a sort of an unhappy marriage. And they continued to correspond throughout their life. You could tell that I think Catherine really wished that she had been able to wait for William. But that didn't happen.
So did they get into a math duel?
Well, with the Reverend, he would have died. I mean, Hamilton was an insanely good mathematician.
So back to the whole exam here. So after the one exam, what if you failed the exam?
You're out. Yeah, I mean, it depends. If your family could pay for your room and board, you didn't fail the exam. There's a thing that there's a notion they still have today, the gentleman's C, which means if your family is endowing something at Yale, you're going to get a lot of C's. Then one day you can become president.
Dang.
That's all right.
Yeah.
Bars.
That's great. So he regaled Catherine with a lot of poetry over the years, and whenever he became sad, he eventually did marry, but it sounds like it wasn't a happy marriage. They had kids, so obviously they were I don't need to go there. But the wife would leave and go off and live with her mom for like 10 months at a time, or go visit England with the children, and he was alone a lot of the time. So in those periods, he'd start writing poetry to Catherine. And then the other thing besides poetry is he had a problem with booze. I've never understood this. A Scottish guy who drank a lot. It's weird.
Unheard of.
But it really became a problem. Like, he was at one point he was in a scientific meeting and got lit up and really embarrassed himself. And so he had, at that point, he realized that this was an issue, and he went on the wagon for 2 years straight. And then peer pressure. Some jerk was making fun of him for only drinking water. So he went in, started up again. He died at only the age of 60, which strikes me as likely
What's a wagon?
the alcoholism.
What's a wagon?
Oh, you never heard that? Go on the wagon means to stop drinking.
And when you start drinking again, you fall off the wagon.
I heard it fall off the wagon. I heard it fall on.
Well, you gotta get on before you can fall off.
I'm not following your logic here.
So let's talk about what he did rather than his personal life a little bit. There's three major topics that I would like to cover, although his work involves a lot of other stuff. For instance, I'm not going to mention optics, but he did some impressive work about optics, the theory of rays. Hamilton circuits and graphs is the first one. So he proposed a problem. Yeah. Oh, I forgot to bring it on. What's up?
Dr. Kennedy's talk on Hamilton's walk thing.
Yeah, that's it.
Oh.
So what is a Hamiltonian circuit? We talked previously about Euler and the Eulerian circuits, which are circuits like the Königsberg Bridge problem where you cross all the edges once. Well, Hamilton just flipped that around and said, well, what about a circuit where you have to touch all the nodes once? And he proposed this as a contest problem. So have people seen a dodecahedron before? It's 12 sides, they're pentagons. I'm going to try my best to draw it.
Oh yeah, you brought it in for the other dice, the dice stack.
There's a pentagon on the northern hemisphere, right at the Arctic Circle, and from that you'll have pentagons that dangle down. Whoops, that's a foregon. And then there's also pentagons that poke their way up from the Arctic Circle. Can you see that? So what you want to do is imagine a pentagon on the bottom, another pentagon on the top, attach pentagons all around those, and then let them drop down from above and rise up from below until they all meet in the middle. So you get this zigzag line around the equator where all the pentagons run into one another. That's a pretty complicated shape. If you're much more careful than I was just being, you can make a good sketch of it. But what Hamilton asked them to do was find a circuit that goes through the edges of this thing and touches every node. And that drawing is really a problem because you can't see most of the nodes. Or there's a bunch of them that are on the back side of the picture. So it turns out the problem was really trivial if you make the following transformation. If you can look at this thing instead of from a distance so that you're seeing it like this, you want to put your eyeball right, I'm going to try to draw an eyeball, right there, just like an inch above that face, and look at the thing. So that you're looking into the interior of it, and you can see everything as if it were on a flat. In other words, you project from there.
So it's a planar thing.
You turn it into a planar thing by projection. There's a name for that kind of projection. It's called stereographic projection. You take a sphere and from the North Pole project out through the points on the sphere. It actually proves, interesting point here, the sphere has a surface area that's finite, right? But by stereographic projection, you project it onto the infinite xy plane. The same number of points in a finite sphere as there are on an infinite xy plane. Doesn't that mess with your noodle a little?
It's a little mind-bending.
It has infinite sides. Makes sense.
But the other one's finite.
So that's infinite sides.
It's not circle, but it's anyway. So if I try to draw that thing in the way we're talking about, the upper face there would become a really gigantic pentagon because it's really close to us. And these pentagons that surround it would have edges that came in from there. So far I've got 3 sides almost, so I need 2 more. I think they look sort of like this. I'm going to make them curve the wrong way. I know you're thinking, oh, that's wrong. But this line that I'm constructing right now is the equator of our sphere. Did I end up with 10 points around for? Is it 10?
9.
You have 10 lines.
And I better have 10 points too.
Did we count one line, one node twice?
No, that was 10. Okay. And then lastly, we need to have the other pentagons come in. They come in from these guys. And they meet at the other pole. Is that north or south? I guess that's the southern hemisphere we're looking down there in the middle. All right. So on this picture, if you switch things around and you make that picture, can you find a circuit like Hamilton wanted? Now remember, you don't have to use all the edges. You just need to visit all the nodes.
I'm gonna say yes.
Yeah, it's actually not too hard to do. You just have to use a little forethought. So, like once you kind of go into the interior, you need to leave yourself a little way to get back out. If I do that, so. I'm going to go around the outside. Keep going more that way. Oh, this is going to be okay. Come back down that way. There's many. Actually, but so Hamilton proposed this as a contest problem, probably for one of those horrible tests at the end of the term, right? And I think nobody got it. But the point was that it showed he was thinking about graph theory, and it's, you know, okay, so this seems trivial. It's like, okay, you've got a solid, you're asking a sort of a made-up question about it, but it's not quite as trivial as you might think. This is a real problem that people have to solve in real life. They call it the traveling salesman problem, which is you've got a map of cities and roads connecting them, and somebody has to figure out not only a route that does like this, that visits all the cities he's got to go see, but he'd ideally like to drive the least amount of time. Okay? So you want to figure out a route that's like this, that actually has the shortest total lengths of the roads. These roads were all length one, so it's not a big deal to solve the traveling salesman problem. The traveling salesman problem is an interesting problem because it's in a category that's called NP-complete, which means nobody has figured out a way to solve it in a reasonably fast way. But we do have a way, if somebody shows you the answer, you can check that it's the good answer. It's a strange phenomenon. It's also been pointed out to me by the living mathematical hero of mine is a guy named John Conway, who teaches at Princeton, no longer teaches at Princeton. Conway pointed out that if you build a model of a network of roads with string, and the lengths of the string tell you how long the roads are, if you just pick it up and dangle it, the part that gets taut, that becomes tight, is automatically the Hamiltonian path, the traveling salesman route. So it's a weird problem in that the physical world will answer the question for you, but we don't have any math that will answer the question for you. Okay, so that's Hamilton circuits. Another thing named after him, he called them characteristic functions, now known as Hamiltonians. There are sort of two approaches to dynamical systems, and the easy one is Hamiltonians. There's another one that's maybe it's Dirichlet. But anyway, there's another formulation that's really hard, and I don't do dynamical systems, so I'm not going to pretend to know it. But what Hamiltonians are is something that behaves the way potential energy does. You know how potential energy works in a real simple system? Let's do a pendulum. So you have a pivot point up high, and you've got a long strand, and then there's a weight on the bottom. It's fairly heavy, right? And the idea is the pendulum swings back and forth. You actually have two numbers that you want to keep track of. It seems like maybe a single number would do. What's the angle, or where's the horizontal position of the pendulum? But there's one parameter, is position.
Changing light.
Whether you measure it with angle or with say the x coordinate of that bob at the end. There's another parameter that's almost equally important, though. It's how fast the thing is going. What's its speed? So the second parameter is velocity. I said speed at first, but it's really velocity that you want, because you'll pick a direction and say, like, this way is positive, so if it's heading back, it's going in a negative speed. And the two of these together form what's called state space. So if you tell me the position and the speed of the thing at any time, I know exactly what state it's in. And I can tell you from there how it's going to evolve. If you only tell me the position, I may not know what's going to happen next. Like if I'm right here in the middle of the swing, right? And now, you know, you're looking at a frozen image of the pendulum, right? And you're about to unpause the video, right? Which way is it going to go?
Who knows?
Who knows? It depends on which way it was moving before you could pause, right? So that velocity is important. If you know both of them, though, you do know what's going to happen next. So in state space, let's call it position and position's derivative. We start out, say, with the position here at negative. That is, starting the position, the guy out here. And it begins to move towards position 0. Well, what happens to its speed as we go that way?
Oh, is this the electron thing?
No, this is a weight on the end of a rope. Speed begins to increase. Is that way positive?
Yes.
Yes, so it's starting to move this way, but it's moving up also this way. When it gets to 0, it's going as fast as it's ever going to go, isn't it? And then as you head towards the, have you ever ridden swings, people? You know, now we're heading towards the other high end of the swing, and we slow down, and we slow down, and when we get to the end, we stop. That is, in state space, our path does that. Our x-coordinate, our position continues to increase, but our velocity begins dropping until it hits 0, just as we hit the actual position. And then, you know, the thing comes back around like that. So if you plot this guy in state space, it's not a pendulum going back and forth. It's a circle in the p prime plane. And what is it that makes that circle the special thing that it is? It's the Hamiltonian. Which is the total energy of the system. So what kinds of energy does a system like this have? There's two pieces. There's one that's called potential energy, because that's a heavy ball at the end of the rope. And if it's up in the air, it's got energy due to the, you know, well, if it's up in the air, you had to pick it up in the air. Like, you know, have you ever had to take a heavy friend and pull them back on the swing until you're ready to release them? Or, you know, a bunch of people get on the swing and you have to drag them back. It takes work to do that, so you're putting energy into the system. The other thing is kinetic energy. Okay, so does everybody know the formulas for these things?
Potential is MGH.
Potential is MGH. Okay. We're going to call it, you know, even though x here isn't the direction that goes up, it's some function of x, isn't it? And in fact, okay, I'm going to write MGH for a second. How is h related to x if we're on this circle or on a pendulum?
As x increases, h increases.
If x doubles, does it double? Is this a linear relationship? Well, in fact, it's circular, right? So that's complicated. People usually go, well, you know, I could do it with a parabola. And so a quick thing to do is to approximate this with the position squared. What is kinetic energy? This I don't know if people know. It's 1/2 mv squared.
Oh, yeah, I need
Have you run into that? But wait a second. V squared? That's what I've been calling p prime. So that's p prime. So the total of these is the sum of something times p squared plus something else times p prime squared. That's the equation of an ellipse. I drew it as a perfect circle, but in fact what we've got is an ellipse, because it depends on these numbers, the 1/2, the m, and the mg there. But nevertheless, you find that this thing, the system, by thinking about the total energy, has to move around on an ellipse in the state space picture. And that's probably the simplest example of a Hamiltonian. Now, somebody mentioned quantum mechanics, electrons.
Yeah, as you know.
There's a quantum mechanical formulation of all this. The energy in an electron is also from different components, and you have a Hamiltonian that describes it. There they call it the wave function of the electron. Actually, I think that's the square. And I'm probably missing that up. Don't ask me quantum mechanics stuff. Go talk to Matt Angelo. But anyway, this idea of a Hamiltonian, which you can define for lots of different systems, is just some function of the coordinates that is preserved. This total is always the same. As the potential goes down, the speed goes up. And as the speed goes down, the potential goes up. So you're just seeing energy flow back and forth between these two types, but not get destroyed. That's the idea of an invariant. Lastly, quaternions. 5 minutes to talk about quaternions.
Good luck.
So where is the steady state on the state space? Where would it go to?
Well, it just keeps running around the circle. Or the ellipse, right? So if you're in a frictionless setting, that is a steady state. It just turns around. So quaternions. Hamilton had presented a paper that explained how to think of complex numbers as pairs of real numbers. And everybody knew that in a certain way, but he made it algebraic. He realized that there was a way to think about the complex numbers in algebraic terms of pairs of real numbers. So it's literally, his innovation there was to think about complex numbers as being the points in an XY plane. Yeah? Prior to that, people had thought of complex numbers as the solutions of certain kinds of equations, but they didn't have the understanding of what algebra is. Having done that, he naturally wanted to see if he could do the same thing with 3 space. Can I take 3-dimensional space and figure out how to add points and subtract points and multiply points? What am I going to do to multiply these points? So he apparently spent lots and lots of years working on this problem. So much so that I think I mentioned this previously to you, his kids would tease him about it. Daddy, you figured out how to multiply triples yet? No, he had. And so he was walking with his wife to a meeting of the Irish Royal Society of Science, and he finally made the connection. And this is one of those moments, it was literally his eureka moment. He said it was as if an electric spark jumped in my mind. The circuit was closed, and the idea finally hit me. And on the spot, he decided he would write down these equations. The only thing nearby was a bridge. And it's a stone bridge, a Brougham Bridge. Supposedly, he's on his way to a fancy meeting, and imagining in good clothes. He gets out chisels and starts carving this stuff into the... I don't believe the story. I think he had to come back later with tools.
Isn't that like illegal? Was really start carving the bridge?
Well, he was a upper crust sort of guy. Nobody...
Mathematicians make their own
randomly
laws.
have the tools to carve. I can see chalk.
He might have had a pocket
or-
knife,
yeah.
but what kind of stone was this thing made out of?
Yeah, exactly.
So I'm thinking he remembered, this is the spot, I've got to memorialize this, came back later and defaced the bridge. Now apparently there's a plaque, you can see this, the plaque that says this is the bridge that Hamilton defaced, but you can't really see the markings. So what did he write down? Well, first of all, the big realization was that 3 dimensions wasn't enough. He needed 4. And so we have a real part and 3 distinct imaginaries. So whereas before we had a real part and just an imaginary part, he has to have 3 of them. Okay, so the real part is dealt with by saying there's a unit, number 1, and I can have any multiple of 1. So really thinking about these parts of the thing is about specifying the units. The imaginary things, well, the old imaginary unit was I, so we'll keep I for that. But he needed 2 more imaginary units, so he just picked the next letters, J and K. So a quaternion is something that you can get by putting multipliers in front of these things and adding it up. That's the official definition. People usually write them as fancy H like this. What is this? It's A and 1 plus B times I plus C times J plus D times K. Where A, B, C, and D are in the real numbers. So that's the set he's dealing with. The things that he carved into the bridge are these equations, which he wrote down that I squared and J squared and K squared are all equal to minus 1. And then if you take I times J, you'll get K. But the other part of this electric circuit closing in his mind was realizing that it couldn't be a commutative operation. That in fact, if you did J times I, you'll get the negative of K. Yeah? So that's part of it. But there's more that actually I think you can use these to deduce the rest. If you do J times K, you'll get I. And if you do K times I, you'll get J. So for each of those, there's another one that says they don't commute, but in fact it's the opposite of commuting. K times J would be negative I, and I times K is negative J. So I feel like we've got to do one of these. Do you want to do a multiplication of some quaternions?
Sure.
Okay, first off, what would you do to add two quaternions? You add the corresponding bits. Real parts get added, the I parts get added. So that's vector addition. In fact, people are used to that. What if I have just an arbitrary expression with the i's, j's, and k's, something like 3 plus 2i minus j plus k. And then I want to multiply that by something. So how about 1 minus I plus 2j minus 4k. I just was trying to make up numbers as we went.
Set up that matrix.
Yeah, we should set up the matrix, really. But you can also do it with the distributive law. This is 1. I don't want to assume commutativity, so you have to watch this out. Carefully copy your first term and times it by 1. And then subtract that same thing, 3 plus 2i minus j plus k times I. I'm distributing them in from the left, right? I'm taking this whole business and popping it in there, and then in there, and I haven't done it yet, but I'm going to go into there next. So that would be plus 3 plus 2i minus j plus k times 2j. And then finally minus 3 plus 2i plus, minus j. I'm sorry, this is taking up forever just because I have so much to copy, times 4k. Cool?
Isn't that third term minus?
The third term
Plus 2j.
plus 2j from there. So, no, that's right. Okay. Now each one of these needs a distribution. This one is not hard because 1 multiplies in, we just moved over. But this guy, you need to multiply I in from the right. Remembering you don't have commutative rule anymore, so you have to always keep that in mind when you're dealing with quaternions or other groups. So I comes in here on the right, and there on the right, and there it won't matter because I, and then finally there on the right. Okay. I guess I won't finish. Hamilton viewed this mess as an aid to calculation. Do you feel like this is going to be an aid to calculation?
It certainly doesn't seem like it.
It doesn't seem like it, but you know, if you programmed it and got a computer to do all this stuff work for you, then maybe it is. The great debate was between Hamilton and an American mathematician named Gibbs. And Gibbs kind of liked the idea But he said, look, we don't need to go to 4 dimensions, and we don't have to have, you know, the real part in there. What you need is I, J, and K, and they're the X, Y, and Z axes for stuff. And have you guys done cross products? That's Gibbs. He stole it from quaternions. If you stick to just the I, J, and K things, what's called a pure imaginary quaternion, you get Gibbs's vector calculus stuff. So that's where you get the sort of easy computations. Anyway, the other, just briefly, the other thing I should mention is, remember the 4 square theorem?
Yes.
Figure out what is a quaternion times itself, and you'll see that you end up with squares in all the terms. And that means that the 4 squares are those 4 numbers that, you know, every number can be expressed as the sum of 4 squares. It means that the lengths of quaternions take every possible value. You can really reinterpret 4 squares in terms of quaternions. That's the modern approach to thinking about it. Sorry, we're late. So, no class Wednesday. How do you think?
Last Friday.
The last week.
The last paper, we talked about it last time. If you were here, I'm going to ask you to do another biography.
You just said you would expand.
Oh, I did say I was going to expand it. I will do that. A bio of a modern era mathematician. So somebody from the Renaissance forward. This should be up around 8 pages now. What else do we need to say about it? References. There should be references. If anyone still having trouble with BibTeX or LaTeX, let me know. And I will help you. I think there were a few people that still have BibTeX. Before the year is over.
That's helpful.
Well, I'm assuming you might want corrections, so that means you have to have time to grade it, and then the corrections you should do on the final, but.
No, I don't think we'll have corrections on that page. Yes, we're going to have.
Which year?
Is it gonna be like your testing quizzes so far?
What'd you say?
Which year?
The one we're in. So no, I think I would like to have it those before finals week. The last day of class would work. If you want to knock it out and have it to me early because you've got other things going on, I understand that.